Hello viewers, in this session we will solve some problems based on the theory covered so far. Like in the previous review problem session, please try to pause the video after each question and try to solve it yourself before looking at the solution, which I will anyway present here. Okay. So, let us start with problems. Okay. So, the first question is as follows. Question 1, it is a very simple question. Let us try to look at a contour integral. Okay. So, a very simple contour integral. So, evaluate integration over gamma e raised to z squared by z minus I power 4 dz, where gamma is the circle, okay, as the circle of radius 4 centered at the origin, okay, described in the positive direction, that is the counterclockwise direction once. So, that is the question. So, I will present the solution. Okay. So, this question is a simple exercise in Cauchy's integral formula for higher derivatives of analytic functions. Okay. So, clearly if you try to use the parameterization of gamma to actually compute the contour integral directly, it will be rather tedious. Okay. So, it is easier to use Cauchy's integral formula. Okay. That is the point of this exercise. Okay. So, you should recognize the integral as an integral of a certain form. So, if you consider f of z equals the numerator e raised to z squared, okay, then this integral gamma integral over gamma e power z squared by z minus I power 4 dz can be thought of as an integral of the form f of z by z minus a power 4 dz, okay, by the Cauchy's theorem version 3. Okay. So, if you have or the deformation theorem, the integration over that kind of curve gamma of f of z by z minus a power 4 dz is going to be the same as integration over this circle C A R f of z by z minus a power 4 dz. So, you have the following situation, you have I here, okay, and you have a circle of radius 4 around origin. Okay. So, that is not to scale, but that is the picture. So, this is a circle of radius 4, that is your gamma. Okay. It is not a circle centered at I, but that does not matter. By Cauchy's theorem version 3, we know that integration over gamma of f of z by z minus I power 4 is dz is equal to the integration over a circle of radius r, okay, circle of radius r around I, r small enough, let us say 1, okay, f of z by z minus I power 4 dz. Okay. And once again this by the Cauchy's integral formula for the derivatives is 2 pi I times the third derivative. We have a fourth power in the denominator. So, it is the third derivative of f at the point I, okay, divided by 3 factorial. For higher derivatives, we had the following formula, integration C A R, okay, f of z, there are constants here, there are constants 2 pi I, okay. So, n factorial divided by 2 pi I times integral over C A R of f of z by z minus a power n plus 1 dz. Okay. So, that is the Cauchy's integral formula. So, here we apply with this with n equals 3 to get this. Okay. So, if we compute the third derivative of our f at I and substitute it here, we are going to get the value of this integral. Okay. So, the third derivative of f itself is easy to compute. Well, f is e power z squared, f prime of z is z squared 2 z e power z squared, f double prime of z by the product rule is 2 e power z squared plus 4 z squared e power z squared. Okay. So, the third derivative of f is 2 e power z squared times 2 z 8 z e power z squared plus 8 z cube e power z squared. So, 4 plus 8 12 z e power z squared plus 8 z cube e power z squared. Okay. So, f triple prime at I is 12 I e power minus 1 plus 8 minus I. So, this is minus 8 I e power minus 1, which is 4 I by e. Okay. So, that is your f triple prime of I. Okay. So, substituting that in here, we get 2 pi I by 3 factorial 6 times 4 I by e, which is minus 4 pi by 3 e. Okay. So, that is your integration over gamma of f e power z squared by z minus I power 4 dz. Okay. So, that is the solution to this problem. The next question is as follows. Okay. So, let f of z be an analytic function or be analytic on the unit disk and suppose that the modulus of f of z is less than or equal to 1 by 1 minus modulus of z for each z belongs to. Okay. So, under these circumstances, try to show that the modulus of the nth derivative of f at the point 0 is at most n plus 1 factorial times e. Okay. So, the key here is to use an appropriate contour in the unit disk, okay, so that we can bound the nth derivative. Okay. So, more precisely we will choose an appropriate a circle of appropriate radius, so that the nth derivative at 0 can be bounded by the values of the function f on that circle. Okay. So, please pause here and try to see if you can come up with the solution, and here I will present the solution. Okay. So, as I said, the idea is to choose an appropriate circle. Okay. So, if gamma is a circle, okay, oriented in the positive sense. Okay. So, positively oriented, okay, mod z is equal to 1 minus 1 by k. Okay. Let us decide what this k is a little later, let us just to see. Okay. So, then what we get is the modulus of f of z, okay, on gamma, on the circle gamma. Modulus of f of z we know is less than or equal to 1 by 1 minus 1 by k, which gives us k. Cauchy's integral formula for the nth derivative, okay, at 0 is given by, well, f n of 0, okay, is n factorial by 2 pi I times integral over gamma. This particular gamma will work because f is analytic inside and on this circle, okay, of f of z by z power n plus 1 dz. Okay, that is the Cauchy's integral formula for the derivative nth derivative of f at 0. So, the modulus of the nth derivative of f at 0 is less than or equal to n factorial divided by 2 pi integration over gamma of the modulus of f of z divided by modulus of z power n plus 1 mod d z. Okay. And on gamma we have bounded f of z, it is bounded by k, we will set this k shortly. Okay. So, this is less than or equal to n factorial divided by 2 pi times integration over gamma of k divided by, well, mod z is 1 minus 1 by k. So, I have 1 minus 1 by k power n plus 1 mod d z. So, on gamma, okay, z is equal to r e power I theta, where r is equal to 1 minus 1 by k. Okay. So, theta goes from 0 to 2 pi. Okay. So, if that is the parameterization, then d z will give us r I e power I theta d theta, okay, or mod d z will be r times mod d theta. Okay. So, this expression here is less than or equal to n factorial divided by 2 pi times integration over gamma. Okay. Now, we have converted everything into theta. So, theta goes from 0 to 2 pi of k divided by 1 minus 1 by k power n plus 1 times 1 minus 1 by k, which is r here, okay, and then modulus of d theta. Well, we can take that to be d theta itself. I mean, it is not the modulus, it is the absolute value. Okay. So, we can take that to be d theta itself. Okay. And then this we see is after some cancellation, we see that this is less than or equal to in fact n factorial divided by 2 pi integration from 0 to 2 pi k power n plus 1 factor here cancels with the denominator. Okay. Something like this, 1 factor here cancels with 1 factor here. Okay. And so, we get k power n going to the top. So, we have k power n plus 1, which is k power n here times k divided by k minus 1 raised to n, okay, and then d theta. Okay. And then this is less than or equal to n factorial divided by 2 pi. Well, now is the time to set k. Okay. So, or let us still decode this. This looks like k by k minus 1 power n times k times d theta. Okay. And since we want to show that this is bounded by this nth derivative at 0 is bounded by n plus 1 factorial times e. Okay. So, in order to get that n plus 1 factorial, probably correct to take k equals n plus 1. Okay. So, that k and this n factorial give us n plus 1 factorial. Okay. So, this is take k equals n plus 1 rather. Okay. So, this is less than or equal to n plus 1 factorial divided by 2 pi, okay, times integration from 0 to 2 pi of n plus 1 by n power n, okay, and then d theta. Okay. This is, of course, this is a constant which is clear of the integration. So, we can actually put it outside the integration, okay, and this is less than or equal to n plus 1 factorial divided by 2 pi times 1 plus 1 by n power n and then 2 pi. The integration from 0 to 2 pi of d theta gives us a 2 pi. So, we can cancel these and get this is less than or equal to n plus 1 factorial times this factor 1 plus 1 by n power n. Okay. And we know that this is a sequence 1 plus 1 by n power n, okay, is an increasing sequence, okay, of real numbers, okay, and one proves in a first course in real analysis that this tends to E. okay, the limit of this increasing sequence, either one defines that to be E, or if E is defined otherwise, then one proves that that converges to E. Okay. So, in any case this is an increasing sequence. So, before we go to the next problem, we will introduce some terminology, okay, namely convex set and the convex hull of a set of points. Okay. So, let us start with a convex set. Okay. So, a set is said to be convex if it has the property that if x and y belong to the set, then the line segment joining x and y belong to the set. Okay. So, a set S is said to be convex Okay. So, for simplicity we will assume this is a subset of C. Okay. So, a set S contained in C is said to be convex if whenever x comma y belong to S, then the line segment joining x and y is contained in S. Okay. So, another way to say this is, well, one can always parameterize a line segment by T x plus 1 minus t times y. Okay. So, t between 0 and 1 will parameterize the line segment joining x and y. Okay. So, if this belongs to S, this point belongs to S for t between 0 and 1, whenever x and y belong to S, then you say that S is a convex set. Okay. So, for example, convex sets could look like this. Okay. So, a line segment itself is convex, because if you take any two points on the line segment x and y, the line segment joining them is contained within this line segment. So, it is a convex set. Okay. So, likewise, if you take a triangular piece like that, okay, and then the inside of this along with the boundary, that is a convex set. Okay. So, you pick any two points x comma y inside the set. Okay. They could be on the boundary, for example, the line segment joining them is contained in the set. Okay. So, this is a convex. In general, the inside of the polygon, okay, along with the boundary of the polygon, if you wish, is a convex set. Okay. So, that is a convex set, and then there is the concept of a convex hull. So, in order to consider a convex set which contains a bunch of points, we can construct a convex hull which has an additional minimality property as well. Okay. So, here is a convex hull. The convex hull of a set K contained in C is a convex set S contained in C, okay, containing K. Okay. So, it contains K. Not only that, it is such that no proper subset of S contains K. Okay, no proper convex subset, I should say, no proper convex subset of S contains K. Okay. So, such things are normally constructed as follows. Notice that, so note the intersection of two convex sets is convex. In general, the intersection of a collection of convex sets is convex. Okay. So, since this happens, what you do is you consider the set of all convex sets which contain a given k and you take their intersection. Okay. So, let G be a collection of all convex sets containing a given set k. Okay. Then the intersection of all these. Okay. So, intersection of S such that S belongs to G, okay, is a convex set by the above note. Okay, is a convex set containing K. Okay. And by construction, this is the convex hull of K, because no proper subset of this will contain K, because if there were a proper subset of this which contains K, then it would belong to the sub collection and then it would appear in the intersection, okay, and then so it would be the intersection or a superset of the intersection. Okay. So, that cannot occur. So, there is no proper subset of this which contains convex subset of this which contains K. Okay. So, that is how we construct a convex hull. Okay. So, and is a, so I will remark here that this set intersection S belongs to G, S is a convex hull of K. Okay. So, that is how we construct convex hulls. So, we will note one property of convex hull. It is as follows, or couple of them. Okay. So, the convex hull of a finite number of points in C is a polygon. Okay. So, this is intuitively clear. Okay. So, depending upon how many of them are collinear, etc., okay, the geometry of the polygon differs, okay, but eventually some or all of them are going to be the vertices of the polygon. Okay. So, suppose some point is like this, some point is like that, then these three are collinear, etc. So, then eventually you will get a polygon which will be the convex hull of a bunch of these points. Okay. So, we will not prove this property, but this is true. Okay. And then it's one can actually try to prove this property by taking coordinates, etc. Okay. So, this is easy to do. Okay. So, you just have to use the definition of a convex set and of a convex hull to prove this. Okay. And then the next property that I want to state is that let x 1, x 2, so on until x n, okay, belong to a convex set K. Okay. Then S 1 x 1 plus S 2 x 2 plus so on until S n x n, okay, belongs to K whenever 0 less than or equal to S I less than or equal to 1, and the sum of S i's S 1 plus S 2 plus so on until S n is equal to 1. So, this is once again easy to prove using the definition of a convex set. Okay. So, one can show that this point, okay, for any values of S like this is belongs to a convex set K. Whenever these points start, when you start with these points in a convex set K. Okay. In particular, if you consider the convex hull of these bunch of points, it is a convex set. Okay. And so, then this kind of combination, okay, where SI's are like this, okay, is also a point in that convex hull. Okay. So, with this we are ready to now state the Next question. Okay. So, let z1, z2, so on until zn be zeros, be the zeros of a polynomial p of z. Show that the zeros of the derivative of p lie within the convex hull of these zeros, okay, of the points z1 through zn in the complex plane. Okay. So, consider using the quotient p prime of z by p of z to prove the same. Okay. So, hint, use p prime of z by p of z. Okay. So, try to solve this problem and I will provide the solution here. The statement of this problem is called the Gauss-Lucas theorem. Okay. So, the solution is as follows. Let alpha be a 0 of p prime of z. Okay. If alpha is one of the zi's, okay, then it sure lies in the convex hull, because the points themselves lie in the convex hull of those points. Okay. So, if alpha is one of the zi's, then alpha lies in the convex hull of z1 through zn. Okay. Now, suppose that alpha is not a 0. Okay. So, if not, okay, so suppose now that p of alpha is not equal to 0. Okay. So, alpha is not one of the zi's now. Okay. So, in this case, let me first write p of z as some constant c times, perhaps a constant c times z minus z1 times z minus z2, so on until z minus zn, because such a factorization is true for p of z, because these are all the zeros of p of z, z1 through zn are all the zeros. Okay. So, perhaps there is a multiplying constant c there, c belongs to c not equal to 0. Okay. So, c belongs to c minus 0. Okay. And suppose p of z is like that, okay, then p prime of z is easy to calculate. P prime of z, each time you take the derivative of one factor which is 1, okay, and use the product rule. So, I can actually directly divide by p of z to get p prime of z by p of z is equal to 1 by z minus z1. So, the factor which is missing in p prime figures in the reciprocal like this, okay, and then there are p prime is the sum of all these factors. So, it is plus 1 by z minus z2 plus 1 by etcetera, so on until plus 1 by z minus zn. Okay. So, then since p of alpha we are assuming is not 0 now. Okay. So, then p prime of alpha by p of alpha is equal to 1 by alpha minus z1 plus 1 by alpha minus z2 plus so on until 1 by alpha minus zn, okay, which is equal to 0, because the numerator p prime of alpha is equal to 0, alpha is a 0 of p prime by assumption. Okay. So, so this is equal to 0, okay, and then we will use this equation to do the following. So, we will use this particular equation. Okay. So, first multiply the numerator and denominator of each of these terms with the conjugate of the denominator. Okay. So, we get alpha bar minus z 1 bar divided by modulus of alpha minus z 1 squared plus alpha bar minus z 2 bar divided by modulus of alpha minus z 2 squared, etcetera, plus alpha bar minus z n bar divided by alpha minus z n modulus squared is equal to 0. Okay. So, alpha bar times, let me factor out an alpha bar, I get 1 by modulus of alpha minus z 1 squared plus 1 by alpha modulus of alpha minus z 2 squared plus so on plus 1 by modulus of alpha minus z n squared. Okay. And this is equal to, on the right hand side I will collect these terms z 1 bar divided by modulus of alpha minus z 1 bar, etcetera. So, on the right hand side I get sigma, okay, I or k equals 1 through n, okay, of z k bar divided by the modulus of alpha minus z 1 z k squared. Okay. So, now notice that this is a real number, let us call that a, okay, and the coefficient of z k bar is also a real number, okay, and so let us call that a k. Okay. So, this is a k, 1 by this is a k. So, alpha bar times a is equal to sigma k equals 1 through n z k bar a k, okay, where a k is equal to 1 by modulus of alpha minus z k squared. Okay. Also notice that the sum of a k's is actually equal to a. Okay. And so, a k by a is such that a k by a is in between 0 and 1, these are all modulus of numbers, complex numbers. So, they are positive or 0, okay, and since the sum is equal to a, sum of a k is equal to a k by a is in between 0 and 1, okay, and sigma a k by a is equal to 1. Okay. So, this is where, okay, the second property of the convex hull that I mentioned is coming into picture. Let me go back. Okay. So, this SIs, so these are the candidates, a k by a's are candidates for SIs. Okay. So, alpha bar, so I will conjugate on both sides of this equation, a and a k are real numbers. Okay. So, the conjugation does not affect them. So, what I get is alpha is equal to sigma k equals 1 through n of z k times a k by a. Okay. So, now we recognize that this is a combination like in the property 2. Okay. So, this is a combination which lies in, so this lies in, this complex number lies in the convex hull of z 1 through z k or z n rather, okay, by property 2 above. Okay. So, which is what we want. So, alpha lies in the convex hull. Okay. So, alpha lies in the convex hull of z 1 through z. Okay. So, in either case, whether alpha is a 0 of p of z or not, alpha lies in the convex hull of z 1 through z n, which proves the problem. Okay. And this, like I mentioned, this is called the Gauss-Lucas theorem. So, the next question is as follows. Okay. So, this is an application of the Gauss-Lucas theorem. Show that the zeros of the polynomial p of z is equal to 1 plus 2z plus 3z squared plus so on until n z power n minus 1 lie inside the unit disk B01 bar. So, the solution is as follows. Okay, so, try to see if you can work out the solution and I will present the solution here. Okay. So, notice that P of z looks like the derivative of z plus z squared plus so on until z power n. Okay. So, that prime means a derivative. Okay. So, P of z can be thought of as the derivative of that polynomial, okay. And then we will use the Gauss-Lucas theorem, okay, which says that the zeros of P of z lie in the convex hull of the zeros of this polynomial. Okay. And so, let us concentrate on this polynomial within the parentheses. So, this polynomial can be factorized as z times 1 plus z squared so on until z power n minus 1, okay, which is z times, we will recognize that as z power n minus 1 divided by z minus 1. Okay. And we recognize that this z power n minus 1, the roots of this polynomial z power n minus 1 are precisely the nth roots of unity, and when we divide by z minus 1, we forget the root 1 itself. Okay. So, if zeta k is equal to e power 2 pi I k by n, okay, 1 less than or equal to k less than or equal to n minus 1, okay, then zeta k is a root of this polynomial z plus z squared plus so on until z power n. Okay. And notice that 0 itself is a root of this polynomial. Okay. So, 0 is also a root of z plus z squared plus so on until z power n. Okay. So, now the zeros, these are n minus 1 in number, okay, and 0 is including 0, we have n roots, and an nth degree polynomial has at most n roots. So, we know all the n roots, these are all distinct, that is the point. Okay. So, we now know all the roots of this. Okay. So, the zeros of the given polynomial, okay, of P of z lie in the convex hull of the set zeta k, okay, which is e power 2 pi I k, like I have mentioned here. Okay. So, this is zeta k such that 1 less than or equal to k less than or equal to n minus 1 union 0. Okay. But now, what is the convex hull of these? Well, the roots of unity lie on the unit circle. Okay. So, they divide the unit circle into equal number of circular pieces. Okay. So, these zeta k lie, okay, they look like e power I theta for some theta and lie on the unit circle. Okay, and 0 is in the center. Okay. So, the convex hull of the roots of, okay, of this set, okay, of the roots of z plus z squared plus so on until z power n, okay, is the unit disk. Okay, is actually is a subset of the unit disk. B bar 0 1. Okay. So, if k equals 3 for example, okay, Okay. We are looking at the third roots of unity, and when you forget 1 itself, okay, when you have this and 0, okay, the roots of z plus z squared, okay, when n is equal to 3, we have z plus z squared plus z cube. Okay. So, so this is an example, z plus z squared plus z cube when n is equal to 3, you get this is z times 1 plus z squared. The roots of these are omega and omega squared, okay, the cube roots of unity, which are here and here, okay, and then you have 0 itself, which is the root here. So, the convex hull is going to be this triangular region. Okay. So, this is an example. Okay. So, likewise, you are going to get a subset of B bar 0, B01 bar, the closure of B01, okay, and that is the convex hull. Okay. So, the zeros of P of Z, okay, definitely lie, okay, in B01 closure. Okay. So, that is a solution to this problem. These kind of questions are a standard. Okay. So, suppose f from G to C is analytic. Okay. So, I should start with let G be a region. So, G is a region, and suppose f from G to C is analytic, and suppose that f of z is real for all z belongs to G. Okay. Then show that f is constant. Okay. So, a real value analytic function has to be a constant function. Okay. So, there are other versions or other kinds of problems which look like this. Okay. So, one can ask that show that if modulus of f of z is constant, then f is constant. Okay. Or one can ask that if f of z is purely imaginary always, then show that f is constant. Okay. And one can more generally ask that if the values of f of z lie on a line passing through origin, for example, or on a straight line, then show that f is constant, etc. Okay. So, all these will follow from a theorem which we will do in the next few sessions, called the open mapping theorem, which says that an analytic function should take open sets to open sets. Okay. So, or a non-constant analytic function should take open sets to open sets. Okay. So, if f were to be non-constant, it will take G, which is a region, which is an open set, to an open set. Okay. So, what that means is that so it cannot take, in particular it cannot take C to the real axis, which is not open in the complex plane, okay, or a part of real axis, any part of real axis which is not an open set in the complex plane. Likewise, it cannot take the complex plane to particular circle for that matter, okay, where the modulus is fixed. Now, we can use Cauchy-Riemann equations directly to show that f is a constant. Okay. So, for now, since we do not have the open mapping theorem at hand, we can use the Cauchy-Riemann equations to show this problem. Okay. So, here is the solution. Okay. So, let z naught belong to G, okay, and let so f of z is equal to, or f of z naught is a real number, okay, that is given, f of z naught, f of z is real. Let S equals the set of all z belongs to G, such that f of z is equal to f of z naught. Okay, we will show that S is the whole set G. Okay. So, firstly let us look at f of z, which looks like, let me separate it into its real and imaginary parts, which looks like u of x y plus I times v of x y, and u and v satisfy the Cauchy-Riemann equations. Okay. It is given that f of z is always real, which means v of x y is identically the 0 function. Okay. So, on G. So, this is u of x y plus I times 0. By the Cauchy-Riemann equations, we have, what do we have? We have v of x y is 0 implies u x, the partial of u with respect to x is 0, and the partial of u with respect to y, which is minus the partial of v with respect to x, that is also 0. Okay. This is 0 because u x is equal to v y, okay, and v y is 0. So, both these are 0, and since G is a region, there is a rectangular path connecting, there is a R path connecting z naught and z. So, using that rectangular path, you can try to recover u of x y, okay, by integrating along by integrating along the line segments parallel to x axis. Okay. So, on x axis, okay, line segments parallel to x axis. So, I will just not say that, I will just say on z naught z, this is to indicate the rectangular path connecting z naught and z, okay, and then you can integrate with respect to y partially. Okay. So, dx, and then on the line segments connecting z naught and z, okay, on the rectangular path connecting z naught and z, on the line segments which are parallel to y axis, okay, or y axis rather, okay, you can integrate with respect to u y with respect to y. Okay. And but these both of these are zeros. Okay. So, which means both of these are given to be 0, okay, and u x anyway is 0 on vertical line segments, okay, and then u y is likewise 0 on horizontal line segments. So, actually identically 0 in the whole region. Okay. So, this gives you the constant of integration, that is all. Okay. So, two constants of integration. Okay. So, so u of x y is constant. Okay. So, likewise, well, that already shows that f of x y is a constant, a real constant. So, that is a solution to this problem. Okay. All right. So, the next problem is as follows. So, let u from C to R be bounded harmonic function, and suppose that u is a real part of some analytic function f, okay, on all of C. Okay. Then show that u is bounded, u is constant rather. So, what that means is show that u is a constant function. Okay. So, use the real part of f for every complex number z. Okay. So, try to solve this problem, and I will present the solution here. Okay. So, let me first remark that it can be shown that this supposition is unnecessary. What I mean by that is this is additional, but since we did not show that in the theory, we will assume this in addition to u being a bounded harmonic function. Okay. So, since u is the real part of f, Okay. For every z belongs to C, what you can do is you can consider e raised to f. Okay. E raised to f is analytic, or in fact, it is entire, because f is entire. Okay. Since f is entire, this f here in the problem is entire. Okay. So, the modulus of e raised to f is going to be e raised to the real part of f at every point z, and that is e raised to u. Okay. So, since it is given that u is bounded, okay, so this is less than or equal to e raised to m, okay, where u, okay, is bounded. So, the modulus of u, or the absolute value of u, is less than or equal to m. Okay. It is a bounded function. So, there is such an m. Okay. So, e raised to f is a bounded entire function. So, by Liouville's theorem, we know that e power f is a constant function. That immediately implies that f is a constant function, and which in turn shows that the real part of f, u, is a constant function. Okay. So, it is also an easy exercise. Okay. So, here are a few more problems. Okay. So, here is the question, find all z for which cosine z is real. Okay. So, the solution, well, you just have to look at the expression for cosine z. This is e power I z plus e power minus I z by 2, okay, and then this is real number. Okay. So, we have to use the fact that real number is equal to its conjugate. Okay. So, we will use that fact. Let us first see what this is, e power I z plus e power minus I z by 2. This is equal to e power I x minus y plus e raised to minus I x plus y divided by 2. This is equal to, well, this is cosine x plus I sin x divided by e power y plus cosine x minus I sin x times e power y divided by 2. Okay. So, this number should be equal to its conjugate, okay, for the above condition. So, so this number cosine x plus I sin x divided by e power y plus cosine x minus I sin x times e power y divided by 2 is equal to its conjugate. The conjugate of this is going to be cosine x minus I sin x divided by e power y plus cosine x plus I sin x times e power y divided by 2. Okay. So, upon simplification, well, these cosine x's cancel, these cosine x's cancel, okay, and then you are left with 2's cancel, of course. Okay. So, you are left with 2 I sin x divided by e power y is equal to 2 I sin x e power y. Okay. So, you end up with the equation sin x times 1 minus e power 2 y is equal to 0. Okay. So, well, either sin x can be 0. So, this is 0, this product is 0 if sin x is 0, or if e power 2 y is equal to 1. Okay. Sin x is equal to 0 has the solution x equals n pi, where n is any integer, okay. And then e power 2 y is 1 implies 2 y has to be 0, which implies y is 0, which is the real axis. We know that cosine is real on the real axis, okay. And whenever x is n pi, even then your cosine z is real. Okay. So, these two give you the set of all points where cosine z is real. Okay, and we will end this problem session with this problem.